Okay, today and the next day's topics might seem kind of dumb. You're gonna preface this. It may seem odd. You probably are gonna have the question, why would you do this? Okay, if that thought comes to mind, that's okay. Okay, I promise I can probably give you like some better reasons, but you gotta be patient as to why we're gonna do this. Okay? So I want to preface this with a question. I've got 3 different graphs, all in different colors here, and if you guys can, I want you to try to figure out how they're related to each other. Anyone had a chance to look at this yet? Or how are these 3 graphs related? Okay, I'll give you a hint. There are points on the graph that have been like enhanced by actually using a dot. Consider how like the dots are related to each other. Okay, I'll give you another hint. Consider what a function means. A function means that I give you an input and you give me back an output. So why don't we just consider an input? Someone give me a number. 2. 2 is a better number because 4 is not going to be on this graph. Here is where 2 is. How do the inputs at 2 relate to each other? Now, I guess we're going to have to figure out the red one, but one of them is at 4, one of them is at 5, and then where's the last one? Probably up here at 9. Let's try another input. 1. Where are these outputs at? 1, 3, and 4. If you have any ideas yet. I'll keep going. Let's try another input at 0. At 0, it looks like our outputs are at 0, 1, and actually the blue line and the red line are actually both at 1. Nothing yet, eh? Okay, the title of today's notes are operations. What does operations mean in math? Add, subtract, multiply, divide. Four plus 5 equals 9. 1 plus 3 equals 4. 0 plus 1 equals 1. So how are these graphs related? The red graph is the sum of the other 2 graphs being added together. Does that make sense? Well, I mean, let's just keep looking at points then, right? And seeing whether this logic holds. So what are the points that we have for the input values here? We have a -1, we have a 0, and we have a 1. Now this is kind of tricky here because we got to make sure we add the right 2 graphs together. I said the red graph is actually what happens when you add the other 2 graphs. So if you add the dark blue graph, -1, and if you add to that the positive one, you end up with the red graph, which is 0. Keep going. Let's just make sure with one more that it works. Here we have a -3. Up here we have a 4. So if you take a -3 and you add a 4, it ends up giving you a 1. I prefaced today's lesson by saying if this sounds kind of stupid, I mean, it's not all that purposeful yet. Well, I guess I'll say why we're going to do this. Eventually, the goal here is that I wanted to show you guys new functions, right? New graphs. Well, one of the ways that we can get new graphs is by taking smaller graphs and adding them together. Does that make sense? Exactly. So if I give you a graph of one and a graph of another, we can add them together. So this may seem kind of basic when we start, and that's kind of the point. But we took a blue graph right here, which was linear, and we took a light blue graph right here, which was quadratic. And what type of graph did it make when we were done? Quadratic. Watch this then. Look at the equations. One of the graphs was x squared. And to that x squared graph, we added the 2x plus 1 graph. This plus this give that. You see how that works? Like this is graph number 1. This is graph number 2. and collectively it made a newer graph. Now, when we do this with very basic functions, it's going to make graphs that you already know. But eventually what's going to happen is if you take, like, say, a quadratic graph and multiply it by a cubic graph, it's going to make a lot more complicated graphs. Does that make sense what I'm going for here? It becomes even worse when you divide. If we were to, say, take a linear graph and divide by a quadratic graph, it's going to make a very odd-looking graph. Does that make sense? And so that's where we're going next, is in order to make different and new-looking functions, we need to start adding and subtracting them together. Because really at this point here, you guys should hopefully be familiar with a constant function, a linear function, a quadratic function, and then yesterday we started talking about, like, well, this might be what a cubic function looks like. And this guy right here might be quartic, and this guy here might be quintic. Does that make sense? So now our goal is to take what we've learned yesterday and start combining them. So again, the topic of today's notes, operations. We're going to add, subtract, multiply, and divide graphs from each other and see what those graphs then look like. Does that make sense? Okay. Again, if it seems kind of pointless, I mean, it's not the most useful thing we do in math, that's for sure. But, so here are some typical examples of how we might notate this. Okay. If you wanted to add some graphs together, you know how I've talked to you guys about how, like, there's f of x, meaning that's like your y values? Really what we did there is we took our y value, we added another y value to get a third y value. Here's the problem. I can't just do f of x plus a different f of x because, like, how are we going to know which graph is which? So often what we start doing is picking new letters of the alphabet. So rather than functions always being f bracket x, eventually we're going to start adding g bracket x and h bracket x. So what this really means here is take the y value for one of your graphs, take the y value for another one of your graphs, and literally add them together to get a y value for a third graph. Does that make sense? But we just need different letters. So often you'll see f's and g's and h's and j's, and again, who cares? All it means, if you ever see this notation right here, is to find a y value, find an output. Another way of writing it then, rather than writing f of x plus g of x, sometimes you might see it written like this. So what this basically means is find the y value for the f graph, find the y value for the g graph, and add them together. That work? So likewise, subtract. We can do subtract. Eventually we'll also do multiply and divide, but let's just work on subtracting them. So let's try to sketch by hand a couple of functions, and then we want to figure out what would happen if we added them together. So what kind of function is this first one here? Linear, quadratic, cubic? Linear. How do we know? The degree is, we don't write it there, but there's a 1 there, right? Yeah. It's degree 1. So, do you guys recall how to graph a linear graph fairly quickly from, like, way back in grade 9 or 10?
This is like the negative 1 is the y-intercept and negative 2 is like the slope.
Fantastic. That's it. That's probably the fastest way of doing it. So, negative 1 is your y-intercept, so I'm going to plug that value right there. And then 2 is the slope, so that means, like, go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and let's see, over 1, down 2. By the way, if you guys happen to have, like, a pen and a pencil, or, like, 2 different colors, it might be helpful in doing this just to keep them straight. So I'm just going to notate that I'm going to use purple for the f of x graph. Does this make sense then why I'm just picking a different letter for the other graphs just to keep them straight? So g of x means that it's still a function, it's just, we're just using another letter. So using that same logic then, I'll use red here. This graph right here in red needs to have a y-intercept of negative 2, and then it has a slope of 1. Does that make sense? So negative 2 is the intercept right here, and it's going to have a nice slope of 1. Normally, I would suggest you probably are going to need to actually draw a line through it, but I'm not going to draw a line through it today just because I think it's going to make it's going to get really messy in there. But normally I'd say take a ruler and draw the line through it. But I think this will do for now. We'll just do it with dots.
The slope was 1.
The slope of the red graph was 1, yeah. So what this last thing right here means, I'm going to do this one in green. I'm going to ask you to find the third graph. And the third graph is the sum of adding the y values together. So, why don't we start right in the middle at 0? Actually, maybe I should give you guys one more second. I think everyone's not plotting. Okay, so let's start here at 0. One of my graphs gives me a -1. One of my graphs gives me a -2. So if you like my vending machine analogy, it's like you decided to go to one vending machine and buy a -1 something. You went to another vending machine and decided to buy a -2 something. So how much do you have total? -3. So that would be right here. Let's hold off on that for a second here, the equation. Here we have a +1, here we have a -1. So if you add those together, it would be +1 and -1? Yeah, right here at 0 in the middle, yeah. Here we have a 0 and a 3. So adding 0 and 3 would give you 3, yeah. Here we have a 1 and a 5. So that would give you 6. I've drawn 4 points. Do they look like there's kind of a pattern to them? Yeah, it looks like it's still linear. Let's just do one more point because I think I'm going to run out of room. Here I've got a 2, and I believe what is a 7. So that should be up here at a 9, I think. And then I'll go backwards. I believe both of these points are directly right on top of each other. So -3 plus -3 should be down here at -6. I'll draw a line through this one. What sort of graph did we just produce? Like, I guess what type of graph is what I'm saying. Linear, quadratic, cubic? Linear, yeah. And now let's prove it by using the equations. One of the equations was 2x minus 1. And we were asked to add to that x minus 2. Oops, that must be a 2 there. What happens when you combine this stuff together? What stuff can actually like combine like terms? Well, the 2x can go with the x, can't it? So what does that give you? 3x. And then you have a -1 and you have a -2. So you put those together, you get a -3. Is that what we just drew in green? Did we draw a graph that has a y-intercept of -3 and a slope of 3? Hopefully you'd agree. Yeah, look, right down here, here's the y-intercept at -3. And Haley just said a second ago, the slope basically is go over 1 up 3, so that's the slope of 3. Does that make sense? So in this example, a linear graph plus a linear graph gave us a linear graph. Does that make sense? Again, when we start, this is going to be very, I don't want to say boring. Like, it's not going to produce anything really crazy. What will happen eventually is when we get to multiply and divide, then it's going to make some graphs that look kind of different. Does that make sense? So you just have to bear with me because I kind of want to go through things step by step. Did that follow, by the way? Go. Okay, so maybe a bit of a different challenge here. I'm going to draw 2 graphs for you just to save some time. I just pulled this out of a textbook somewhere. Let's try to subtract the 2 graphs from each other. And then once we're done that, let's try to figure out what the equation of that graph might be. So again, what this means is take the f graph, and f of x means the y values. So find a y value for the blue graph. Find the y value for the red graph. And by the way, make sure that it's based on that same x value, though, right? Like, you can't use this y value right here with this y value right here. That's not fair, right? So like you've got to subtract this y value from this one. Right? And let's see what the graph does. You guys can probably start if you want. I'll just work on it too. I'm going to start way over here. What is it? It's blue minus red. So over here I've got a -3, -1. So that means I should be down here at -4. Then I've got minus 2, minus 0. So that should still be minus 2. Then here I have minus 1, minus 1. Minus 1, minus 1. Good, 0, yep. I see a bit of a pattern starting. Okay, now keep in mind, we're doing blue minus red. So now blue is actually on top of red now. So 0 minus 2. 0 minus 2 is actually adding 2, so we're up here. And hopefully you're starting to see, hey, this is making a linear graph. So I'll just do one more point. 1 minus 3 should give us 4. So look, it looks like this actually produced us a nice linear graph. So let's try to write the equation. I'm going to say that f of x minus g of x, its equation appears to be linear, so I need to figure out the y-intercept and the slope. So what's my y-intercept look like in this? Y-intercept? Yeah, 4. 4, way up here. And what's the slope of this purple graph? 2. Yeah, there we go. 2x plus 4. Does that make sense? Again, we're not talking the most purposeful math in the world. Don't get me wrong. Like, this is not something you're ever going to do on a daily basis. But the goal, again, is to try to take basic functions, like linears and quadratics, operate them together, and make something more complicated. Any questions?
So like when we subtract one line from the other, we're just using one point.
We have to use a consistent point. Like if you're going to use an input of 2, you have to use this y value, subtract, say, this y value. But what you can't do is like use this y value of 3 and subtract this y value of negative 3. Because that's not fair. Here you input 2, but here the input was at 0. Makes sense? You almost have to like consider it like in a line here as to how we're going to add and subtract. Okay. How's this going so far? Can I kind of skip ahead then and go to something maybe more challenging? Because I want to move ahead here. If you guys get the idea, why don't we find the multiply one then? Adding and subtracting is fairly basic. Multiplying becomes a little bit more challenging, and it becomes interesting. Well, hopefully. So we're going to do the exact same thing. We're going to multiply the g of x value and the f of x value and see what it produces. So let's start over here at the lowest numbers I've got. We've got a 1 and a negative 3. So when we multiply 1 by negative 3, we get negative 3. So right on top of the blue one. Here I've got a 0 and a negative 2. But anything times by 0 is 0. Here's where it's going to change up a little bit. We have a negative 1 times by another negative 1. That makes it positive 1. Previously, we started to have a nice little slope. Not anymore. Let's do the next one. We've got a 2, a negative 2, and a 0. What's happening? It is. It's making a parabola. Yeah. And I'll explain why it's making a parabola in a second. But good catch there. We've got a 1 and a negative 3 again. So that makes it back down here to negative 3. Let's just do one more. I don't think there's much room for anything else. 2 and negative 4 would give you negative 8. So hopefully you guys can recognize this shape. Parabola shape. Shut up.
If you're doing, because I'm doing it with just the equations.
So
I'm writing the equations with just either one.
Yep.
So would you almost have to FOIL?
Yes, that's actually the point I wanted to make. But yeah, let me do that in a second. Yeah. Okay, everyone's cool with this being a quadratic? Yeah, I want to do basically what Sean was describing here. If we had to make an equation for the blue graph, would it make sense that the equation for the blue graph would be y equals, what's the slope? 1x plus 1? Would that make sense? That's the equation for that one? And then for the red graph, it's going to have a negative slope, so it'll be y equals negative 1x minus 3. Well, what happens when you multiply graphs together? You're actually going to end up foiling them. If you took 1x plus 1 and multiplied it by negative 1x minus 3, if we wanted to figure out the equation of the new graph we just made, we're going to foil it. And so, long story short, if you take a linear and times by a linear, it actually will make a quadratic. So it would give you negative x squared, which is good because we actually know that it's upside down. It would give you negative x, negative 3x, and negative 3. So you'd have negative x squared minus 4x minus 3, and that would be f of x times g of x. Does that make sense? So linear times by linear actually gives us quadratic. So far, so good. Awesome. Okay. Talk about multiplying somewhere in here. If you want to do multiply and divide, then here's a couple ways of writing it. Typically, we do f of x directly next to g of x. We don't want to use the times sign. Like, don't do this. Don't do f of x, x, g of x. I would say try to stay away from that just because this x right here refers to an input. And like the times sign of x, it's kind of confusing. So like try not to do that. I mean, it'll still work. But usually we just write them directly next to each other. Or here's another notation. This one right here means take your y value for the f graph, times it by the y value for the g graph, and just make sure that you're doing it for the same x. So like when I was saying to like you were a few minutes ago there, you can't like have this value right here getting added to this value right here. That's not fair. What you can do though is this one and this one because they're for the same x value. Does that make sense? Okay, so let's get to the really difficult one, the kind of the point behind this lesson. The one that makes very unique and tricky graphs is the quotient one. Because I think like with most things in math, adding and subtracting and multiplying are probably the things you were probably best at when you were younger. Dividing is a lot worse for a couple of reasons. Okay. Let's give you some just made up numbers. If I ask you to add 1 and 2, it's 3. If I ask you to subtract 1 and 2, it's negative 1. If I ask you to multiply them, right? What happens if I ask you to take 1 divided by 2? Now we're going to get some decimal values. Right? Or, here's another problem. What if I ask you to go 0 plus 2? Not a problem. 2. 0 times 2? Not a problem. What if I ask you to go 2 divided by 0? Can you do 2 divided by 0? 0 divided by 2 you can do, but you cannot divide by 0, right? And it makes like an error state in your calculation. And so the main graph I want to focus on then is the quotient graph. You cannot let the bottom of this graph right here be equal to 0 because you can't go 2 over 0. That's just not permissible. So why don't we skip ahead and find the divided by ones. Actually, let's do this slide here. This one's not a bad one to try. So let's say I were to give you two equations. Let's try to find the equation for f times g of x. So, I mean, since we didn't actually have a graph going on here, literally what I want to do is just take these two equations here and FOIL them into each other. So, like the f equation is x squared plus 4x plus 3. And we're going to times it by the x minus 2 equation. Do you guys remember how to do like a FOIL when it's like 3 against 2? Just make sure that everybody times this by everybody. So like make sure that you do this guy times that one times that one, this one times that one. And then also do this one times that one, this one times that one. Does that make sense what I'm saying? Okay, so you'll have x to the 3, you'll have 4x squared, you'll have 3x, then you'll have minus 2x squared, you'll have minus 8x, and you'll have minus 6. So putting it all together, you'll have x to the 3rd plus 2x squared minus 5x minus 6. That is what h of x is equal to. So if you take a cubic, no, I'm getting ahead of myself. If you take a quadratic f graph and times it by a linear g graph, what kind of graph do I get when I'm done? A cubic. That make sense? Let's use some color here. All right, good on multiply? Okay, let's get to divide. Divide's the trickiest one of all. Take the f graph and divide by the g graph. Wow. You can't like divide FOIL. So often what we'll do is we'll write it like this. We'll write the f graph on top of a fraction, and we'll write the g graph on the bottom of the fraction. This is what h of x would be for this guy right here. But I'm actually not done. Do you guys remember how like the top of a fraction, or like how a polynomial here, how sometimes we can factor and do some canceling? This one right here can actually be factored. You could write it like this. It's actually x plus 1, x plus 3, all over x minus 2. Now in this example here, nothing will actually cancel. But it is actually possible that you could actually cancel some stuff. Does that make sense?
So this one just stays the same?
This one will just have to stay there, yeah. But do you get where I'm going here? Is that it is actually plausible in some examples that based on our factoring of stuff, some stuff could cancel. And that's what makes the dividing, when we do this, kind of the trickiest one of all. What if you do g over f? Yeah, just switch it around. In this one right here, it would just be that your h of f graph looks like x minus 2, and it would be over top of the x plus 1 and the x plus 3. Grab a graphing calculator. We're going to graph these things and see what they look like. I don't want to graph the purple one. You guys probably should know roughly what a cubic looks like, right? A cubic is going to do a kind of thing. However, what is this red graph going to look like? Okay, so that's our goal going forward now, is now that we're going to start combining functions together, it's going to make some very weird looking graphs. Okay. One thing I would recommend is maybe put the whole top of the fraction in a double bracket, like x plus 1, x plus 3. Like I'm going to put the whole top of a fraction in an extra bracket, and then put the whole bottom of the fraction in another bracket. So hopefully it looks something like this when you type it in there. Okay. Let's graph this thing. Here's where it's going to start looking kind of odd. Anyone get something that looks something like this?
I didn't get that line.
Okay, that's because I have an older style calculator up here than you guys. This line right here actually does not exist. We talked last year about something called an asymptote. Do you guys recall doing reciprocal graphs where it looked something like this? If you graphed it, it looked like that. That sound familiar? There are certain values that x cannot be. And in this graph right here, the one thing that x cannot be is the number 2. Why can't it be 2? Well, right there on the bottom of that fraction, if you try to go 2 minus 2, you can't. Because then you'd have 0 on the bottom. That makes sense. My calculator is trying to draw in an asymptote right here. But this is making the graph look very odd then, because you can't have values there. There is actually a graph over on this side of the graph. We just can't see it. We might need to manipulate our graph a little bit more. I might recommend going on your window size and go like maybe minus 30 to 30, just so we have a little bit bigger. You could zoom out or something like that too if you want. But here, oops, I think I screwed up. Yeah, should probably go to 30 there. That is a new function.
Like our, yeah, like I could
It's kind of like a funky reciprocal function, but it's not technically a reciprocal. It basically what the graph does, if I could redraw it, is the graph does, and that's our new graph.
My line's not that far.
This one right here. Hopefully you don't even have one of those actually, because only the oldest of calculators actually draw.
He's like,
Yeah.
I was like, is it that?
No, you should, most calculators won't put a line there. So, like I said yesterday and the day beforehand, our goal for math going forward here is we're now going to talk about all sorts of weird and crazy new functions. And I mean, this would definitely fit as this is an odd looking function, isn't it? So, now we need to talk about properties of this graph. Okay. The main properties are going to be domain and range. We should start by talking about those. You know how I told you that domain is almost always an element of the real numbers? Now it's not. There is one number you cannot use. 2. Right? And maybe a way of double checking that is go to, like, say, your table. I'm still at 500 from yesterday. Go to your table set, if you've done that, and make it go back to, like, say, 0. And go up by 1s.
What are we putting there? 0?
2 says error. Okay. So is the domain anything you want it to be? Actually, no. So there's a couple ways you could write it, but here's probably the best way of writing it. You'd say your domain would be x's element of the reals, and you're just going to say, but x cannot be 2. You're basically going to say x can be any number you want except for 2. What about the range? Can you get any single y value you possibly want? Look way down here. Can you get like a really big negative number? Yeah, I guess. And it keeps going up, and it keeps going up, and it keeps going up. But then it goes back down again. There is a gap. Do you guys see, like I'll draw it right here. There's a gap right here to right here where there are no y values in that gap. How do I figure that out then? Any ideas? Tools we might have on our calculator? Fantastic, yeah. Can someone do, can you table right here? Can you guys do this maximum value right here? Try to find where that max is right here. And you table over there, can you guys try to find this minimum value right here? Because we're going to need those to figure out what the range of this particular function is. You may just need to keep moving the cursor like left, no, right, just a really long ways. Like you have to get it past that stupid asymptote. Anybody get a number? Well, tell me what you got and then I'll compare it. And which one are you doing, the minimum one? 4.68. That's the y value, right? You guys get a y value over here for the max?
0.2540.
That'll work.
I have 2.7.
Okay, let me try it here. I'll calculate the maximum first. So that would be here. Okay, so I've got a maximum value right here at negative, no, it's the y value I want, 0.254. So yeah, I got whatever one of you guys said there. It's the y value we care about, by the way, right? And then if we want to do a minimum way over here. Okay. We're all in agreement now? 15.7. Okay, so here's how you might want to write this then for range. For range, it might be just easier to write it like this. Y has to be bigger or equal to 15.7. And y has to be less than or equal to 0.254. It's on graphs like these that domain and range becomes a lot trickier because the graph is kind of weird looking. And that's our goal going forward, is I'm going to start showing you some graphs that are atypical. They won't necessarily be straight lines or parabolas. They're going to look weird. Does that make sense? Let's
What is a minimum and maximum? I couldn't figure it out.
go second. Calculate.
Where do you put the roll of thingies? Like I got to the minimum maximum.
Oh, just.
If you roll it close to like.
So like I would say on the left down here with their shape. Somewhere in that range there is our maximum. But press enter one more time. Okay, you are our minimum. So we need to do maximum for this little bit here. So there. Well, this is the highest point, so use a maximum. You're trying to look for this one here. And this is the lowest point, so use a minimum there. If you use a minimum here, it will work, or use a maximum. So see how I found the highest point there? Then if you use a minimum, use the minimum.
I don't remember it.
Yeah, the minimum would be the minimum of the range you specify. So then that would be the lowest point of that.
Okay. Can we try graphing the other graph then of the two dividing ones? So let me see if I can find my screen again here. Where were we? There it is. Okay. So you guys know how one of our graphs was this red one right here? And this red graph right here, let me just sketch what it looked like real quick. It looked roughly like that. That makes sense? Now my question is, what happens if we divide them the other way? So you know how like 2 divided by 3 is not the same as 3 divided by 2? So let's do the exact same process, only now let's graph this graph right here. And let's see what that crazy thing is going to look like. I would recommend bracket this thing to death. So like I'm going to use a bracket for the top and go x minus 2. And then I'm going to divide by, I'm going to double bracket this. So I'm going to put a big bracket and then another bracket for the x plus 1 and the x plus 3. And I'm just going to go back to a 10 by 10 graph. Maybe you get something like what I have here. Again, you probably don't have these vertical lines. Those vertical lines are asymptotes. What? Go ahead, yeah.
So when you're typing the second,
The equation, yeah.
like the x squared, do we do the x plus 1 again, or do we use the x squared?
You know what? You could have used either. You could have used the x plus 1, x plus 3,
Okay.
or you could have actually used the x squared plus 4, x plus 3. It's the same thing either way. Why are there 2 of these asymptote lines on my graph? There's 2 numbers you can't use. Okay? In this graph here, what are the 2 numbers that we can't use on the bottom? We can't let x be equal to -1, or we can't let it be equal to -3. That's why there's 2 of these things. So this graph looks kind of like a...
Mine's messed up.
Oh, because you're going from 10 to 10, 10 to 10. You need to go negative 10.
Oh.
Does that make sense? You basically told it start at 10, and then you told it end at 10. The calculator basically said, there you go, now you have that.
Okay, I don't want to take too much time here because I think you guys get the concept. Could you guys then solve for domain and range? So let's talk through it a little bit. What would the domain be? Well, what numbers can you use for x? Pretty much anything except for 2 numbers. You cannot use -1 and -3. In terms of the range, again, there's a bit of a gap in here. Do you guys see that gap again where like this is the lowest number it can be? So we would use a minimum to find what that number is, and we'd say it has to be bigger than that. Okay. There's actually an asymptote right here that I think is getting very close to 0. Because like what's happening is this graph is flattening out, and it's going exactly horizontal. So it's kind of tough to determine that and know exactly. So here's a tip I have for students. Know how I told you can go to your table set? Make the table start at a very large number. So like say 100. and then go to your table. What's the y value at 100? 0.942. And maybe do that again, only make your table set, maybe be even bigger, like 10,000. And then see what your y values are. 1e negative 4. You guys know what 1e negative 4 means? Like it's 0.001. What's really happening here is this graph is getting very, very, very close to 0. Does that make sense? However, is it actually touching 0? Okay, so here's how we'd write this. Your domain would be x is any real number, but it cannot be -1 and -3. Hopefully that was pretty straightforward. Your range is going to be this. Y is going to have to be greater than or equal to, I don't know this number right here. Did anybody actually find that minimum number? Like there's going to be a minimum right here. Y is going to have to be bigger than whatever that minimum number is. You guys can somehow find that. Yeah, for that little, like, you know how there's like a kind of a quasi parabola sitting up there? Yeah, what's the y value there?
3.9.
Okay, 3.9 will work. Does that make sense? Y is going to have to be bigger than that 3.9. However, for, you know, these other little sections right here, will those sections actually reach 0? The answer is no. They're getting really close to 0, but they're asymptotes. You guys remember the term asymptote from last year, how it gets really close to it at every section? So then what you're going to say is that y is going to have to be less than or equal to 0. But less than 0. But I don't get to put that little line on the bottom that says equal to, because it's never actually going to touch 0. Does that make sense? It will actually touch that 3.9. So that's why I can put the little bar on the bottom of this one here. But it actually will never quite get to 0 here because of the way the asymptote seems to work. It'll keep getting closer and closer to 0, but should hopefully never quite get there, it looks like. Does that make sense? Like I said, we're going to start venturing into like weird and strange looking graphs. So here's my next slide then. When we combine functions, they become other functions. And so we're going to start basically taking smaller graphs and making stupid, weird graphs out of them. Again, is there a particular point to them? Not really, but I mean, sometimes these graphs actually do have an everyday life kind of use to them. So here's some basic graphs you know. This is linear, this is constant. This can't be a function because it's straight up and down. So I don't know how much time I have left today. Why don't I go right to my very last slide, and we'll just start there and I'll work backwards. Because I don't remember what time we're ending class. Let's do the exact same thing we've done before, because this is the same graph we were working with, like the two graphs here. Let's try doing it by hand. Let's try seeing what happens when we divide these points. So take the f y value, divide by the g y value. So start over here. Here I have -3, and we're going to divide by 1. -3 divided by 1 is -3 still. I should use a different color. Okay, this is where it gets a bit of a problem here. Take 2 and divide by 0. You can't. So probably it's best just to draw that dashed vertical line that implies an asymptote. There's something wrong with our graph right there. We can't do that. -1 divided by -1. -1 divided by -1? 1. 1. Yeah. Alright. Which one is it? We're going to do blue divided by red. So 0 divided by -2. 0 divided by anything is 0. What's next here? Blue divided by red. 1 divided by -3. negative a third, I guess, right? So that's like right here. 2 divided by negative 4 should be negative a half, right? 2 over 4 is a half, but in the negative, so that'd be like right there. What is this? 3 divided by negative 5. So that's like 3 over 5 is what, like 0.6 in the negatives? So that's like a little bit further down, but not much more. What's happening right in this section here? Anyone know? It's doing that flattening out section again, right? What's it flattening out and getting closer and closer to? Any guesses? Yeah, negative 1's the answer. Yeah, I'll just do a couple more to prove it. Here we got 4 over 6, so that's like 0.666 repeating. So that's a little bit further down. And then here we've got like, say, 5 over 7. I mean, if I kept going, it would eventually be like 100 over 102. Is it ever going to be quite 1? No, it's going to be close though, right?
So this other one on this other side would go the other way?
Yeah, what should happen is we should get a 1 on the other side going the other way. We don't have enough points here to keep going, so I'll just tell you what's going to happen to fill in the blanks here. What's going to happen is it's going to go really, really high, skyrocketing like this. And then what should probably happen here is this graph is going to come from very low and flatten out the other way. And so this should look familiar to you guys because we actually did graphs like this last year a little bit. Yeah, it's kind of a reciprocal graph. It's not technically a true reciprocal graph, but like it's going to look something very similar to one. Does that make sense? Cool. Okay. I want to show you something else that might happen here. Because do you guys have the copy of that assignment that I gave you guys? We can actually start doing some questions on there now. Let's say I give you a function, but rather than giving you graphs, I do graphs in class because graphs are very easy to visualize. But graphs are really annoying to draw. Plus, on your diploma, you're not going to be asked to draw anything. So often what I'll do instead is I'll give you like a table of values or some coordinate points. So let's pretend that f of x was made up of these points here, 0, 0, 1, 3, and 2, 5. And let's pretend that g of x was made up of 0, negative 1, 1 and negative 2, and 2 and, pardon me, 7. This should look something similar to one of your assignment questions. What I might ask you to do then is tell me what is f plus g x. So what does this mean to do? It means imagine these points were on a graph somewhere. Keep the same x value, add their y values. So give me an x value that we have in common. 0, I guess. So what happens when you take 0 and you add negative 1? You have negative 1. That would be a point on the new graph. What's another x value point they both have?
1 and 1.
Yeah, 1. And then for the y value, if you took 3 and you added negative 2, you'd have 1. And then the only other x value they have in common is 2. And so if you add the y values, it would be 12. Does that make sense? Let's do divide. F over g of x. So if we did 0, could we divide the values there? Is that permissible? You can go 0 divided by negative 1. That's valid. So it's 0. 1. 3 divided by negative 2. I guess let's just call it negative 3 over 2 then. And then for 2, 5 divided by 7. Let's just call it 5 over 7. One last thing, then we'll probably start packing up here. Sure, the bell's got to go soon. Let's do g over f. Now can I do 0? No. Because I can't take the negative 1 and divide by 0. So here's what we do in that case. We can't even start trying to write a point there. So don't write like 0, comma, error. Like don't do something like that. Like we just don't even bother writing a point because it just doesn't exist. 1 then would end up being what? Negative 2 over 3. And 2 would end up being 7 over 5. Does that make sense? So, long story short now, our goal is to try to make it so that we can take graphs of basic functions and put them together somehow. And in doing so, it's going to make more complicated graphs. And so with those complicated graphs, I need you guys to be able to work with them in like graph form, point form, like I just showed you here, or possibly equation form. Like for example, if I told you that f of x was equal to x plus 1, and g of x was equal to 3x squared plus 9, you could then tell me that g plus f of x would be equal to 3x squared plus x plus 10. Because literally what I'm doing is I'm just adding the equations together. Does that make sense? So 3 main things: point form, equation form, and graph form. Basically be able to get them combined together. Does that work? Okay. Yeah, you guys can... Oh, sorry, what did you say? Yeah, for sure. I don't know when the bell's going today, so... I know, which is odd because how else are we going to be having lunch here? You know, I'm going to call down to the office.
It's Chris. What time are bells going today? Yeah. Okay. Okay, so right now, basically, though. Okay, so wait, we're supposed to change classes. Okay, we'll see you guys on Monday. No, Tuesday. Don't come Monday. I'm not gonna be here Monday. All right, see you guys later.